All right. So thank you very much for giving me this chance to give a talk in this workshop. So in today's talk, I'm going to try to convince you that a gravitational wave detector can be used to look for some interesting physics that beyond the scope of gravitational wave physics. So the LIGO, Virgo, and Kagra, those gravitational wave detectors, or the future higher frequency gravitational wave detectors can be used to look for the dark matter particles in direct detection way. Okay, so the idea was firstly proposed in this paper a few years ago, and then in the paper back in 2019, we used LIGO's O1 data to perform this search, and finally, our theory proposal has been adopted by the LVK collaboration, and a most updated search using the LIGO Virgo O3 data has been carried out as a collaboration work, and is currently under peer review right now. Okay, so before I get into any details, let me firstly tell you what is the most important question in the particle physics point of view. Okay, so this is the table that has already summarized all of the particles that we know existing in the nature. We have this all those quarks, we have the leptons, the gauge bosons, which are the force mediator, and we have this Higgs boson. If you believe quantum gravity, then by discovering the gravitational wave, then you may be able to say that let's add in another spin 2 particle onto this particle table. And the natural question for the particle physicist to ask is whether there is anything else to be added onto this particle table. The answer seems to be yes, because there is very strong evidence to show the existence of the dark matter. Okay, so there are many independent and strong evidence that is all pointing to the fact that dark matter exists in our universe, but we just don't have a clear picture or a good understanding about the properties of dark matter. For example, the galaxy rotation curve, the Bully cluster measurement, as well as the CMB measurement. There are many other measurements related to the evidence of dark matter. Okay, so we know dark matter exists only through its gravitational interaction, but what exactly the dark matter is, what its mass, what its interaction with themselves or with the standard model particles, they are all left to be answered. And here on this slide, I show you the max axis where the dark matter particle may have, which is basically just characterizing the theoretical uncertainty for the dark matter mass. So it can be super light as 10 to the minus 22 eV, or it may not be even a particle. It can be primarily black holes whose mass is comparable to the solar mass. Okay, so in this talk, I'm mainly focused on the ultralight mass regime, where there are a lot of natural predictions. Sorry, there are a lot of string-inspired models predicting the dark matter particles showing up in this ultralight mass regime. Okay, so there are a few good candidates for the dark matter particles in this mass regime. First of all, the dark matter particles needs to be bosons, and the two good candidates, one is the axion, the other is the dark photon. And in today's talk, I'm mainly focused on the search strategy for the dark photon dark matter. Okay, and the key point is to convert the gravitational wave detector to be a multi-purpose experiment. Okay, so what is dark photon? So first of all, in the particle standard model, we know the gauge group of the in our nature, which is the SU3 color times SU2 electroweak times U1y hypercharge. And then it is very natural to imagine that I do have another simple extension to the gauge group beyond the standard model gauge group, which is this U1 prime, and we call it dark gauge group. We call it dark because later I'm going to assume that this gauge group has a very small coupling corresponding to our standard model particles. Okay, so for each gauge group, we introduce the gauge bosons to describe the force mediator. And for this U1 prime, we also introduce a new gauge boson called dark photon. And why it's called photon is just because it's a U1 gauge group. And however, there is a crucial difference that this dark photon has to be massive particle rather than massless, or else it will not be able to play the role of dark matter. Okay, and a further assumption that we have made in this study is to identify this U1 prime to be the U1b or U1b minus L, where B stands for baryon number and L stands for lepton number. Okay, if that's the case, then if the gauge boson is the gauge boson of the U1b, then my dark photon talks to the proton and neutron. If my dark photon is the gauge boson of the U1b minus L, it talks to the proton, neutron, and the electron. Okay, so we know that ordinary material like the mirror in the LIGO gravitational wave detector, it carries a huge amount of dark charge in this way because it has been it is composed by a huge number of protons and neutrons and electrons. So if dark photon plays the role of dark matter, then those mirrors, those test mass, they can feel the force caused by the dark photon dark matter. Okay, and also in this very light, ultra light mass regime, you should think about the dark photon as a oscillating background field rather than each individual particles. And there are many theories that has already demonstrated that the ultralight dark photon can actually play the role of cold dark matter. There isn't any inconsistency in the theory. Okay, so I won't waste you a lot of time trying to give you the background about the gravitational wave detector, but this is just a picture of LIGO, and LIGO has already achieved, all those gravitational wave detectors has already achieved fantastic precision on measuring the relative difference for the arm length. And it really opens the field called gravitational wave astronomy. And as a particle physicist, the natural question for me to ask is whether there is a way that we can actually benefit from this fantastic opportunity and use it to search for the new physics beyond the standard model. Okay, so how to convert a gravitational wave detector to a dark matter detector? So first of all, the LIGO or Virgo, those are very advanced Michelson-Morley laser interferometers. So what they measured is really the relative change or the relative difference of the arm length on the X direction and the Y direction. So if I have the ultralight dark matter, which is properly treated as a coherently oscillating background field, then you can imagine that I have a object that is formed by the dark charge. It carries a huge amount of dark charge. Then it will feel the force caused by the dark photon dark matter. You can imagine that if I put an electron in the radio wave background, the electron will feel the electric force, the electric field that is being carried by the radio wave background, and then it will start oscillation. The same thing can be said for the test objects in those gravitational wave detectors. So those mirrors, as we mentioned previously, they all carry a huge amount of baryon and lepton numbers. So if dark photon play the role of dark matter, then it will feel the dark electric field that being induced by the dark photon dark matter background. Okay, they will start oscillation. They will start oscillating, and because those mirrors are pretty far away from each other, so there is actually a relative phase difference for the displacement caused by the dark photon dark matter background. So that will actually introduce the arm length difference and lead to a observable signal. Okay, so a cool thing about our signal is that it has a very, very fantastic property. So our signal is almost monochromatic because from quantum mechanics, we know that the oscillation frequency is determined by the total energy of the particle. And because the dark matter is moving non-relativistically, so the kinetic energy of the dark matter particle is much, much smaller compared to its mass energy. So the oscillation frequency is mainly just determined by the dark photon mass, and it's a fixed number. And because there is a virtual velocity, because my dark matter is actually moving, not purely perfectly stationary, so there is a spread out of the signal, which is characterized by the kinetic energy of dark matter. And if you do this calculation, you will find that the intrinsic broadening of the signal is about 10 to the minus 6 respect to the central frequency of my signal. So that actually gave us a very easy way to search for the existence of the dark photon dark matter. So what we need to do is just to take the LIGO-Virgo's data and then perform a Fourier transform, translate everything from the time domain to the frequency domain. And all we need to do for the first step is just to look for a bump or look for a spike in the frequency space. And that is actually something very, very easy to be to do. And furthermore, it is possible that one can resolve the detailed fine structure of the signal peak, and that shape of the signal peak is actually predicted by the dark matter Maxwell-Boltzmann distribution, the velocity distribution for the dark matter. Okay, so in principle, there's a very straightforward way to tell the difference between the signal versus some random background that you can actually confirm that this is really dark matter signal, not something else. Okay, so for a very straightforward calculation, you can go ahead and then calculate the size of the signal. As I mentioned previously, that the typical signal is characterized by the relative change of the arm length. So you can calculate, you can take the dark matter energy density, which is taken to be 0.4 GeV per cubic centimeter, use that to calculate the magnitude of the dark photon dark matter background. And with the magnitude of the gauge potential, we calculate the field strength of the dark photon dark matter background. And with that, we can translate that to the force on a mirror, and we can take that to calculate the relative change of the arm length as a function of dark photon mass as well as coupling constant. There is another fantastic property of the dark photon dark matter signal in our proposal. The fact is coming from the fantastic property is coming from the fact that my dark matter particles, they are moving slowly. So the low velocity of the dark matter is causing a large coherent length for the dark photon background. So the coherent length for a signal at 100 Hertz, that is actually about 10 to the 9 meters, which is much, much larger compared to the size of the Earth. So that means that if you have multiple detectors on the Earth, which we actually do, then all those detectors are embedded in the approximately the same dark photon dark matter background, and the signal should be correlated with each other. So rather than look for the signal in each detector, we can actually correlate the data among all those detectors and use that to improve our sensitivity and beat down the background. Okay, so as I mentioned previously, that you just need to go ahead and calculate the correlation among different detectors and use that to calculate the signal noise ratio. So the signal noise ratio can be written in this simple format, and here the lower gamma function is the so-called overlap function describing the correlation among different sites, and the P1, P2, they are just the noise, and the square root of T is just the square root of the observational time for an experiment, which is roughly about a year. Okay, so with all those details being dropped, we can simply perform the estimation about how a gravitational wave detector, how well a gravitational wave detector can be used to search for the dark photon dark matter. So this is our theoretical expectation. So the x-axis is the frequency of the dark photon dark matter signal, and it is one-to-one mapped to the dark photon mass. Okay, and the y-axis is the square of the coupling constant, which is a very, very small number. The blue line and the green lines, those are the current existing constraints coming from other experiments. So for example, the green line is coming from the Atwash experiment, which is the torsion balance measurement, and the green line is coming from the laser lunar ranging experiment. The red lines and the brown lines are the constraints, the 2 sigma constraints or the 5 sigma discovery sensitivities. If you assume the LIGO or LISA, they are operated for 2 years at the design sensitivity. If they find nothing, then the solid line is corresponding to the 2 sigma exclusion region. And on the other hand, if you include all of the lookout square effect, you can actually make a estimation for the 5 sigma discovery region in the parameter space. And the cool thing is that for both LISA and the LIGO, they are possible to make a 5 sigma discovery for the dark photon dark matter. Okay, so that's our theoretical proposal, and then we went ahead and directly used LIGO's data to demonstrate that this proposal actually works. So in this work, back in 2019, we took the LIGO 01 data and then realized this particular search. So I will suppress all of the details. The key point is that we perform the Fourier transform and then look at the power spectrum in the frequency domain. And then we first remove all of the bins that we know there are a lot of contaminations from the noise. So we remove those bins and their neighbor bins. And then we just look for the frequency bins, which has the signal noise ratio whose real component is smaller than minus 5.8, whereas minus is just because the two LIGO background wave detectors at Hanford and Livingston, they are back to back. They are not perfect. They are not aligned with each other. They are actually approximately anti-aligned. That's why we have the negative sign over here. And this is corresponding to the 1% false alarm rate after including all of the 12 factors. And in order to properly model the background, especially to deal with the non-Gaussian noise, we perform some tricks, which is correlating the signal in one frequency being at one detector with the signal at a different frequency being at another detector. So if there is a signal, this signal should not appear in this search. And this is a way to model the non-Gaussian noise. And after do all of those tricks and then remove the artifacts and the broadband correlated noise, we get a distribution for the signal noise ratio, the counts of the signal noise ratio with all of the bins. Okay, so the purple dots, they are coming from the correlation, which are the correlation for the same frequency bins, and the blue dots are coming from the normalized lagged correlation, which is the thing that we use to model the background. So this is our distribution for the signal noise ratio. And over here, we do find a point which seems to be fully consistent with our expectation of the signal. However, this is just corresponding to a hardware injection with a time-dependent relative phase. So if the signal, if the dark photon dark matter signal were really there, then we should have already found it based on our proposed strategy. But the nature didn't choose this this particular parameter space to have the dark matter. So the best thing we can do is to put constraints. So the x-axis is again the frequency one-to-one mapped to the dark photon mass, and the y-axis is the epsilon square. So this is just the blow-up version of the previous plot. As you can see here, that given the fact that we do not find any signal in this search, so the best we can do is to put 2 sigma constraint. And in this small mass window, our using the LIGO 01 data, we can beat other constraints and then start to probe interesting parameter space. So this search is eventually adopted by the LVK collaboration. And then there are a lot of efforts trying to make this, push this dark photon dark matter search forward. So the, as a collaboration work, there are a few improvements being implemented rather than just simply run the same analysis based on to the most updated data, which is 03. So the first improvement is coming from the realization that there is actually another important contribution to the signal, which we didn't include in the previous calculation. And that is coming from the fact that even the mirrors, they are moving in simultaneously, they have this common motion. This can still lead to a observational signal due to the finite photon traveling time. This is the effect that being pointed out by those authors in this paper. Okay, So we include this effect in our signal. And the second improvement that we have is that we perform an independent analysis based on the continuous wave search methodology. And it is a completely different search strategy compared to what I just mentioned. What I mentioned is a strategy that is similar to the stochastic quantum wave search. But now there are additional ways, additional methods trying to mimic the continuous wave search and used to look for the dark photon dark matter. Okay, so with those two combined together, we finally reached our updated sensitivity in the dark photon dark matter background, parameter space. So as you can see, that the mass window that we can probe becomes much larger. The winning is at a much larger mass window, and we carve deeply into the parameter space. Okay, so now let me very quickly conclude. So the application of the quantum wave detector can be extended and used to be search for the dark photon dark matter. And the analysis is actually very straightforward. So far, all the analysis is based on the simple bump hunting search, but there are ways to further improve it. And the sensitivity is actually quite nice. Okay, and eventually let me just show you the acknowledgement to the collaboration. Okay, thank you.